Raise your hand. Who knows what a proppant is? About half the crowd, not bad. I'm going to tell you about stuff that we've been doing since about circa 1982, 83, something like that. But the work didn't start, at least in my interest end of things, for use of these materials as propping agents in oil and natural gas, but rather for a different energy application I'll tell you about real quick. And then it rapidly segued into oil and natural gas materials. The work that I'm going to tell you about here is what we did since 1995 or so at Penn State. Okay. Prior work I did while I was at Sandia Lab. So some of the students who were engaged in this, Walter Lucier got his master's and PhD on this work. Ryan Koseski got his PhD on this work. David's going to get his master's soon if he does a good job on the thesis. Peter is downstairs. He's an undergraduate helping with some of the mechanical properties measurements. And Barry Sheets is one of my colleagues. He's a geochemist, geoscientist. I'm a material scientist and engineer with a background mainly in ceramics and metals. Give you an idea of the kind of things that got us started on this. Funding for this, DOE, Halliburton, Energy Services, Carbo Ceramics, which is the world's largest manufacturer of proppants. They have about 40% of the world share market, okay? And then other little pieces here, there, and everywhere where you can pull it together. And the reason for that is that this particular class of materials, though it's loaded with really good science and engineering to do, wasn't high on the list of the materials engineers as the place to be doing your research in the 90s and 2000s. They're a little bit bigger than quantum dots, and they're not structural materials as people think of them, but I'm going to convince you otherwise that we're particularly well poised here to be a player in proppant research because of work that was done in geochemistry and geosciences from the 40s on at Penn State. This is why I got involved in this. Your husband was employed doing characterization of some of these materials via contract from Sandia to Penn State. So you're talking about 1984, all right? The concept there was that you would have a solar central receiver. This receiver, this aperture right here is 10 meters. This is perched on top of about a 150-meter tall tower, surrounded by a couple thousand mirrors, heliostats, each mirror about the size of this room. The solar radiation is focused in through that aperture, and this falling curtain of ceramic particles was intended to absorb the solar radiation, heat up to something on the order of 1500 degrees C, a 12 million pound batch continuously flowing through there into storage, heat being extracted to do things like crack ethylenes and make chemicals. So this is technology that quite frankly was funded with Carter administration funding. All right? And the concept there was they needed to know what kind of ceramic particle do I use to be able to heat from room temperature to 1500 degrees C in the period of time it takes to fall 10 to 12 meters, all right? And not stick together via sintering when you store 12 million pounds of them hot. All right? So back then we looked at a whole, and it had to be cheap too because the charge here is 12 million pounds. Okay? A train load. Okay? So we got started looking around, we thought about, well, ceramic abrasives like silicon carbide, aluminum oxide, mullite, and so on are relatively inexpensive, widely available. Why not use them? We spent a year working on those. And what we found was angular particles like an abrasive, when they fall 100 meters, indent one another and break the particles into finer particles, creating dust, which sinters the mass together into an 11 or 12 million pound rock. Not desirable. So we rapidly came to the conclusion we needed spherical particles. Where do you get spherical ceramic particles that are refractory inexpensively enough to be able to afford 12 million pounds per application? And the answer came in terms of synthetic proppants, which was an industry that was just starting at the beginning of the 80s. So let me tell you more about what proppants are, and you'll gain an appreciation for why synthetic proppants were important, which ultimately enabled us to do this. And some of the things that we did with this required us to modify optical properties of the materials, which is what you're looking at here. This is solar absorptance as a function of wavelength for materials that we created, synthetic propants, if you will, for this application, but tailored to have certain crystalline phases that absorb solar energy selectively. All right? So we knew from that work in 1984, 85, 86 timeframe that we had a lot of material science and engineering we could do on these materials to alter properties. That segued us right into the oil and gas industry need for profits. Okay? So that's a long-winded version as to why I care about little round ceramic balls. Okay? And they're little. I'll pass some of these around. This is state-of-the-art synthetic proppant from carboceramics here, a variety of different products here that range in strengths from about 60 megapascal diametral compressive strength to about 200. And I'll tell you why that's important in a minute. But those are manufactured from clays and bauxites using a high temperature process known as sintering. What are proppants? When we drill a gas or an oil well and we want to retrieve the hydrocarbons, particularly in a place like the Marcellus, where those hydrocarbons are trapped in very fine porosity, you need to create surface area in the shale or in the geological formation to release the gas to allow you to get it to the wellbore, all right, so that you can retrieve it. That's what the hydrofracturing process does, as I'll show you in a minute. And the purpose of the proppant is to be inserted during the hydrofracturing process to hold those cracks open. That's why they have the name. They prop the cracks open. All right? So they need to be strong. They need to be chemically inert. They need to be cheap because a well, one frac will use about 100 tons. And a typical well pad will have 8 to 12 wells, each one with a lateral, fracking maybe as many as a dozen times, depending on how far out it goes and what their interval is. So the usage of this material is tremendous. The worldwide demand is somewhere between 16 and 20 billion pounds. Pennsylvania's demand for the Marcellus alone at the current rate of drilling is about 2 billion pounds per year. Okay? So the amount of material we're talking about is enormous. All right? Typically, these are small particulates that range about 1/2 to 2 millimeters in diameter, as you can see from the stuff that's going around there. Okay? In the past, we've used everything from, this is frac sand I picked up out of a Unimart parking lot after a frac truck dumped its material by accident. That's what's being used right now. That's cheap. That's $3 a ton. But as David will attest, when you look at that with an SEM, they're angular particles. They're quartz grains. Okay? Very angular. Shards, which will pack. And permeability as a function of time and pressure goes down, which then in turn negates the whole reason you're propping. You want a permeable pad. So the world of synthetic proppants came around in the 80s because they recognized that spherical particles, if they're all monosized, will pack no more than 74% by volume, 26% porosity, and more realistically, 40-something% because they don't pack perfectly, number one. Number two, they flow better because they're round, okay? They glide over one another better, which is meaningful in terms of your frac fluids. You can decrease the amount of additives you need to suspend and move these particles, okay? And you can tailor their mechanical properties by tailoring things like their crystalline phase assemblage, their microstructures, and their finish, coatings, all right? So that's why the synthetic proppant world came about. But all of these materials are still used. Brady and Ottawa sands, like the stuff, that's playground sand, beach sand that I'm passing around there. It's not even Brady or Ottawa. The Brady and Ottawa sands are a little bit rounded because they're glacial. All right, their particle edges aren't sharp. They flow better. All right? That's what's being used right now because the synthetic proppants aren't available in sufficient quantities to serve the worldwide market. Things like fused zircon, that's this. Those are some of the materials I worked on when I was at Sandia back in the early 80s. That company that produced those is now Norton St. Gobain. Okay? That's an electrically fused zirconium orthosilicate. Very complex microstructure because it's made by melt forming and crystallization process. It's a glass ceramic. That is the strongest proppant available in the industry commercially until they quit making it commercially about 5 years ago. But it's also pretty dense. Density is no good. You want it to be low specific gravity so you can suspend it easier and put it where you want it. Okay? Aluminum oxide. There were oodles of companies making proppants back in the 80s. Alcoa, Carborundum, Norton, subsequently Norton St. Gobain, SCPR, goes on and on and on. Aluminum was one of them that was made, and the main application back then was its catalytic substrates for petrochemical processing. All right? Expensive. More expensive than this. Kaolins and bauxites, aluminosilicates. These are the current raw materials for the current state-of-the-art proppants that are manufactured and offered commercially. Now, to give you an idea what some of the properties are, there's your Ottawa sands. You're looking at densities down in this range as being somewhat desirable. We want to go lower than that. I'm going to show you work that we did whereby we made these materials with very good mechanical properties and neutrally buoyant. They float in water, specific gravity less than 1. All right? All the way up through zircon, dense. You better have another reason why you need that. Like you're going to a very deep well where you need very, very high strengths to meet the closure stresses. All right? Why is it important to us here? Well, the worldwide demand for proppants is quite large. Most of it is served by sand. Synthetic proppants are getting a bigger and bigger share. About a third right now of what I quoted you originally as the overall market. There is no supply for the Marcellus Shale. The manufacturing capacity for proppants exists in the southeast and southwest United States, Russia, and China. And part of that is because that's where the bauxite is. All right? And bauxite is the current state-of-the-art raw material. It has the desirable characteristics, if you have great bauxite deposits, to be able to sinter into a high-strength proppant like what I passed around the carbo stuff there. Some of those are kaolin, some of those are bauxite-based. Now, you're here at MCOR, you know something about the Marcellus Shale. Deep, relatively thick, under high pressure, therefore the volume of gas that's entrapped in this black shale is enormous, okay? Absolutely enormous. You've heard all the background and so on, but Terry's basically telling us about 600 trillion cubic feet, retrievable, on the order of 15% retrievable fraction with current technology, 50-year supply of the United States energy demands, the Marcellus Shale alone. And if you look at that last view graph, this would be about the size, when you ratio it accordingly, that the Fayetteville shales are, the Haynesville shales down in Louisiana, and the Barnett shales in Oklahoma. This dwarfs, the Marcellus dwarfs our other natural gas deposits in the United States. And the Marcellus sits above the Utica Shale, which is going to be yet the next play that we're going with. There is no proppant manufacturing capacity in this region. It's a huge opportunity. All right? There are some other opportunities that come along with it. This is the kind of porosity that the gas is entrapped in. There's a half a micron marker. This is very, very fine porosity. You have to create new surface area to get to that gas. And the other unusual thing about the Marcellus, and I stole this from Terry Engelder, this is an outcrop of Marcellus Shale, I think up somewhere up in New York State. Notice these vertical cracks. You know, we think of shales being deposited horizontally, and the fractures will propagate that way. Well, these joints are basically 90 degrees to one another. If you drill a vertical well down through that and don't intersect one of those joints, you're not getting much gas. You have to go across those joints to let them serve as a highway for the gas to your wellbore. All right?